Okay, so second speaker of this morning session is Professor Tilman Pfau from the University of Stuttgart. It's the presentation network, which is a completely different topic, but very interesting, and it's about black hole augmented problems and supersolvers.
Okay, welcome back again. Yeah, as promised, we talked 3 different topics. What you just saw here is a magnetic fluid made of magnetic particles suspended in a colloidal solution. So how this thing looks inside is you have a lot of particles. Yeah. In the case of the ferrofluid, as it is called, these are colloidal particles, so nanometer size, 10 nanometer big magnetic particles. And they show this interesting self-organized structure formation that you've just seen in that movie. Yeah. Of course, I'm not a classical ferrofluid guy, I'm a quantum guy. Yeah. So we want to do exactly the same stuff, or at least related stuff, with quantum gases or quantum fluids. And so we need to have a situation like this, where in addition to the normal contact interaction in a quantum gas, yeah, which is depicted here by the size of that yellow sphere, we also have a magnetic dipole moment in the atom that we are using. And for everything that I'm discussing in this talk, all these dipole moments will be aligned by a strong strong magnetic field. Strong just means a few gauss. Yes, it's enough to keep it polarized throughout the whole experiment. Yes. Now, what we can also do with this magnetic field is we can change the contact interaction by Feshbach resonance, such that we can vary the ratio between the contact term in the interaction and the dipole-dipole interaction term. Yes. So this is the kind of system we are going to play with. Okay. Now here's another movie of that classical ferrofluid. Shows you that these kind of systems, really have a tendency to do fancy things. They can form states like this, yes, which are self-organized in a way and show a rich structure, even in their ground state. I mean, what you have seen here is the ground state configuration of that system. Yes. And we will come to that, what that means for the quantum system at the end of the talk. Now, you have seen that structure formation appears in these classical ferrofluids, like shown here on the left side. So sometimes they look like a labyrinth. These things are called a labyrinth. Sometimes they are forming droplets or dots. Sometimes they are forming an arrangement of voids here, yes, that are connected by the fluid. Yeah. So these kind of patterns, appear not only in ferrofluids, but if you think about it, or you look around you, basically, you find them everywhere. For example, on the skin of animals, yes, here there are dots, here there are voids, and if you look at some other animals like this fish here, the skin has this labyrinth structure. Okay. Or you look out in the landscape, I don't know whether we can do that at the height today. Somewhere in the desert, you can find islands of grass like dots, or you find voids like here, where there's no grass in a certain pattern with a characteristic length scale, or you find this grass growing in a labyrinth kind of structure. Okay. Actually, you find this kind of structures also in other systems like cellular automata or in nuclear physics. There they call this pattern formation nuclear pasta, yes, because of the three-dimensional structure maybe that you find down there. Now, in my talk, I'm going to discuss this in a context of quantum fluids. Yes. Can you have such pattern formation that you find as a consequence, basically, of the description by a nonlinear differential equation? Yes. Also in a quantum system. And I recently had yet another example of such structures being formed. When I was discussing with some mathematical physicists at MIT, they are considering the Grasshoppers Problem. The Grasshoppers Problem, what is that? Think about a lawn that has a certain area, and you have a grasshopper that lands on that area, and now he is jumping a certain distance. Now the mathematical physics question is, how can you maximize the probability that this grasshopper lands again on the lawn? What shape of the lawn do you have to have that the probability for the grasshopper to find the lawn again by jumping in a random direction with a certain distance is maximized? Okay, and it turns out these guys find exactly the same structures. So again, over the hike, yeah, we can really discuss the Grasshoppers Problem. So it's a very general phenomenon, yes. Now, if you do this for a quantum fluid, let's say a superfluid, yes, then basically the ground state of your system shows these kind of structures. Yes, here you see a ground state that is made of dots. Here you see a ground state that is made of a regular pattern of voids, and here you see a labyrinth structure that can also appear for certain parameters. And of course, yeah, if you go from one to the other type of structure, you have to tune something. And what we are tuning is exactly this ratio of contact to dipolar interaction. So, yeah, the dipolar interaction is fun. Yes, I'm investigating the dipolar interaction since more than 20 years. Here you see a classical example of an instability that is caused by the dipolar interaction because the dipolar interaction is attractive, as we have already discussed yesterday. If the dipoles go head to tail, then they attract each other. Yes. So if you have a situation like this, yeah, all these magnets are in the plane, you perturb it a little bit, something dramatic can happen. Yes, and there's an instability, and they get sucked together into a long stick of magnets, as you can see here. Okay. Yes, this is another more controlled experiment with these ferrofluids that was published here by a Finnish group in 2013. Yes, and you see that one droplet of these ferrofluids, if you increase the dipolar interaction, this is what they do by applying a magnetic field, can actually split up transversally into many droplets. Yes. So that is the tendency of that fluid to have a translational symmetry breaking. Okay. Which is the requirement, as we will learn, for supersolid in these superfluids. Here you see the same thing with a little bit different shape of the magnetic field, and then you see, let's say, the one-dimensional version of that fragmentation of the droplet into many droplets into a line or array of droplets in single line. So this is basically what we are interested in, this pattern formation, and the question, can we find a ground state that has translational symmetry breaking, but at the same time is superfluid? Actually, this experiment by the Finnish group, we picked up the challenge. We wanted to repeat this, and here's our version that was done now in our lab. It's very similar, yeah. This instability actually that occurs is called the Rosensweig Instability, and it is a interplay of the dipolar interaction, you know, due to the magnetization of those ferrofluid particles, the surface tension that keeps the droplet together, and in this particular case, the gravity that basically pushes them down. So if you look at this movie, again, oops, let's start it. If you apply the magnetic field, the dipoles want to align head to tail, but then the droplet has to grow against gravity that costs energy. eventually this energy is so large that it's energetically more favorable to split up in two or more droplets. Okay, so breaking the translation symmetry. So now let's come to our system. Our atom here is dysprosium, which has a contact interaction, which is described by a scattering length, whoops, here, and a large dipole moment. Yes, dysprosium has 10 more magneton as a magnetic moment, so 10 times more magnetic moment than the rubidium atom, for example. Yeah. And the interaction goes, of course, like the dipole moment squared, and therefore the interaction energy is about 10 times stronger, 10 times stronger than, sorry, the interaction energy is about 100 times stronger than for rubidium. So, and we have Feshbach resonances in dysprosium, so we can do that tuning trick to have a contact interacting atom, a strongly dipolar atom, or something in between. So we can fine-tune the parameters. That is very important now. Yes. So in a way, you can characterize this dipolar interaction by a length scale. We call this ADD. That goes like the dipole moment squared. And we can characterize the contact interaction by a length scale that is just a scattering length. And the ratio of those two lengths is a dimensionless quantity. It tells you how dipolar is your system. Yes? If epsilon dB, this ratio is larger than 1, then it's dominated by the dipole-dipole interaction. If it is smaller than 1, then it's dominated by the contact interaction, and the dipolar nature is just perturbation, let's say, on the contact case. So if you want to choose an atom to work with, yeah, then the figure of merit that appears here is this. You want to have a large, as large as possible ADD, so it's mu squared, so the dipole moment squared times the mass, actually, here, yes. So if you look at the periodic table, you know, and you color code that figure of merit, then you see, okay, it's favorable to work down here in the Montanite series because they are heavy and they have a large magnetic moment. Historically, though, when I started working on dipolar gases more than 20 years ago, it was not possible to laser cool the lantanides, and we started out with chromium, yeah, which has 6 core magneton. It's not very heavy, yes, as you can see here. So, but the very first experiments on dipolar gases were actually made with chromium atoms, and then after Ben Leff has shown that you can produce a Bose-Einstein condensate of dysprosium, we switched our experiment to dysprosium. And of course, you can also take other lantanides. For example, the Innsbruck group is using erbium here. And I know that in Harvard there's also an erbium experiment going on. So the electronic structure is, you know, they're closed shells. Sorry, they are not, then there are open shells, basically. The open F shell, which basically carry that large magnetic moment, and the 6s shell is basically filled. So the electronic structure is looking more or less like what you know from strontium, terbium, and so on. That is dominated by the 6s electrons. But in addition, you have all that complication by these many F electrons that are in the inner shell. And yeah, we have Feshbach resonances. So we not only have this contact interaction that you see here. Yeah, I don't know. Europe itself is playing soccer, so you should have protection here. And by changing the magnetic field, we can change the scattering length. Okay, so how does the experiment look like? Well, we take a glass cell that everybody knows. We have coils around it, and we have optical dipole traps to shape the container of that gas, basically. Make it a pancake or an elongated cigar or so. We are using green and infrared dipole traps. We have a magnetic field control. It needs to be very precise. And we have a microscope objective up here with a 0.3 numerical aperture. It's not very fancy, but it allows us to observe what is going on inside with a spatial resolution of about 1 micrometer. That's because the observation is happening here on the 421 nanometer to transition to the blue, so the optical resolution of 1 micrometer is easily achieved. Okay, so that is how the lab looks like. For dysprosium, you need blue light and red light for the laser cooling. That's what light shines blue and red here. And in here, up here, there's this glass cell where we're doing all the experiments. Okay. So what happens now if you take a pancake, produce a Bose-Einstein condensate that is flat in one direction and expanded in the other direction, and you magnetize the dipole moments perpendicular to this, like depicted here. If you then look at the dispersion relation, you get the normal phonon branch at low momenta here, like in a contact interacting Bose-Einstein condensate, yes. And you already see a little bit of an effect of the dipolar interaction because this dispersion relation bends down. Now, if you change the scattering length and reduce it, by that you are reducing that scattering length. That means you make the system more dipolar. That small feature in the dispersion relation becomes actually a dominant feature. And the dispersion relation bends downwards and has a local minimum here, which eventually at a certain point touches 0. So when it touches 0, it means it doesn't cost energy to come up with structures at a length scale that corresponds to the inverse Roton k. Yes, there is a finite k. Yes, and what it means is that the systems wants to form structures on that length scale. Yes, if you perturb it with that periodic perturbation with that k, it doesn't cost any energy. Yes. So this is called a roton. Yes. And as a consequence, this initial pancake will fragment into many droplets. That's what you might think about. But if you then think further, and that was what our theory colleagues always predicted, then because these droplets now are elongated cigars, the mean field is negative, and as we have a gas, the prediction was that these droplets should just collapse and disappear. Yes, there should be a violent process. If this roton touches 0, first you fragment, and then immediately, basically, the whole system blows up, just like these magnets that I've shown you in the very beginning. You know, they are attracting each other. They come to very close distance, and a lot of chemistry is happening at the state. Yes. This is this instability on the mean field level that was predicted at the time. Okay. Now, when we looked at this with our microscope objective in 2015, you know, we had done some collapse measurements before with chromium atoms in 2008, so we knew a little bit about this collapse. So we thought, okay, let's do it again and just look again whether this dysprosium also behaves like chromium. And the big surprise in 2015 was, well, the droplets were forming. We see these structures here. Yes, that's a BEC in situ picture now. Yes, but the subsequent mean field collapse did not happen. These droplets didn't want to collapse. That was an experimental finding. Just no theory was done at that time. And very surprising. And when we saw that in the lab, we were scratching our heads. And we first thought we do something wrong here in the experiment. Yes, there must be something that is not working right, and we really checked for months. Yes, our imaging system, is this maybe an artifact of our imaging system, whatever sort, and so on. But it turned out, no, it's real actually. Yes. So we took these pictures of these droplet arrays in this paper here, and we measured their lifetime. They can today they can be around for hundreds of milliseconds. Yes, very stable objects. And it was not so clear where the stability comes from. Why is this stuff stable? Okay. Now the length scale between these droplets is somehow connected to that rotor. Yes, and we will come back to that rotor in a minute. But before we come there, we have to understand why are these things actually stable. Yes. Okay, so this Rosensweig instability is named after this guy Rosensweig, who is the pioneer of this field of ferrofluids. Yes. So we see basically what we have seen in that little movie with classical ferrofluids happens here for this superfluid as well. Okay. Oops. So, okay, sorry. Yeah, this is now the question, what is the roton? I found this cartoon somewhere on the internet. I don't know, I'm not so familiar. Is someone familiar with these masters of the universe? Is this anything that you know? I don't know. I just found this interesting picture about the roton being the vehicle that this guy is driving. No, but the roton is something that actually appears already in these ferrofluids, and you can read about it in the book by Rosensweig here. Exactly what I have said about the dispersion relation of elementary excitations, in this case on the surface of such a ferrofluid, developing a local minimum here. Yes, and if this is touching zero, again, the system will undergo structure formation. Yes. The name of this is a little bit misleading. Yes, it has nothing to do with rotation, actually. Yes. But historically, you know, it comes from the dispersion relation of liquid helium. Yes, here's a measured dispersion relation of liquid helium measured by neutron scattering, superfluid helium. And you see that this also has at a finite k a minimum here at finite energy, not touching zero. Yeah, it has a gap here. And the first interpretation of that minimum here, it goes back to Landau, who interpreted this as the elementary excitations of a vortex spectrum. And that's, I guess, where the name really came from or was motivated by. But later, Noisier, for example, interprets this as a precursor of the crystallization of helium. Yes? So you know, if you are putting some pressure on superfluid helium, then it will form a crystal. And the crystal period is actually what appears here. Yes. You know, helium is the only substance that, if you cool it down to zero at ambient pressure, stays fluid. But in the dispersion relation, you see that it actually wants to be a crystal. It's just not enough. The forces are just not strong enough to bring that roton minimum down and make it a crystal. Yeah. Okay, and in our system, the people that have predicted that roton first, Luis Santos, Maciej Levenstein, and others, have just copied that name. They just call it a roton as in helium. And so this was actually also measured a few years back by the Innsbruck group by Bragg spectroscopy. So they took a sample like this and do Bragg spectroscopy in momentum space, basically, to map out energy and momentum. And they can see a little bit of a minimum here in the dispersion relation that has a gap on the stable side of things. Yes. Okay. But let's now come back to this question, why is it stable at all? Yes. Because it shouldn't be stable. That's on the mean level. Well, we had, again, a lot of discussions, a lot of ideas, what could potentially stabilize these droplets. And to make a long story short, the correct answer is that if you do a mean field treatment of an interacting system, you are neglecting quantum correlations. Yes. Basically, you write down the classical equation with the nonlinear term. Yes. So here is the time-dependent Kosmidayevsky equation, which is the Schrödinger equation that has a kinetic term, a trap potential, and some interaction terms. There's a contact term, which is a local interaction. So it just responds to the local density psi squared. But the dipolar interaction is long range. It falls off like 1 over r to the third power. So you cannot sort of summarize that interaction into an effective change of a scattering length. You have to treat it separately. If the dipolar interaction is weak enough, it's okay to just separate the total interaction into those two parts. And you are neglecting this way any interference between the short-range physics and the long-range physics. That's fine. For weak dipoles, that's not really nice anymore. If you have very strong dipoles, there you have to be more careful. But for now, you just take the kernel of the dipolar interaction, you know, it has this angular dependence and the 1 over R3 behavior, and you integrate that kernel over the whole density distribution. Yeah? And that's where the geometry dependence now comes in. Now it makes a big difference for your local mean field that comes from the dipolar interaction, whether you are in a pancake, where most of your neighbors are repulsive, or whether you are in a cigar, where most of your neighbors are attractive. Okay. So up to this point, we have a normal mean field treatment, and up to this point, the prediction was it should collapse, the whole thing should collapse. Yeah. Turns out, if you go one step further and you do perturbation theory for weak quantum correlations, quantum fluctuations, then you can think about this as a Taylor expansion, and there's a first order correction term that goes not like psi squared, but psi modulus psi to the third power, yes? Or density to the power 3/2. Yes? That is known in the literature for the contact interaction. It's called the Li-Guang-Yang correction since the 50s. And it was calculated for the dipolar interaction in 2012 by Tilman and Pfau. And the interesting thing about this is it has a positive sign. It is repulsive. Yes? So it can stabilize the situation. Now you would say, okay, but this is a weakly interacting system, and in a normal treatment of a Bose-Einstein condensate, you never have to invoke this term. Yes, it's never really doing a big difference here. Yes? However, if you have two interactions in the system, one is repulsive and let's say positive, and the other one is negative, and they almost compensate each other, such that the overall mean field is almost zero. Yes, and just the difference is just a little bit negative. Yes, on the percent level. Yes. Then this term can make the difference because it provides an additional repulsive term that now scales with the density to a higher power. Yes. So if the system wants to contract to collapse, yes, then eventually this term will always win over these terms that just go with the density itself, yes, the lower power. So if you do that model, I mean, we experimentally showed in 2016 by a scaling experiment, different densities and so on, that this is actually the origin of the stabilization. I mean, potentially could have been a repulsive three-body term or something like this, which would scale here not with psi to the third power, but psi to the fourth power, yes, so density squared. But we could rule that out. Yes, that is not happening. Now, as we know this, it's actually interesting to look at this expression of this prefactor. Everything in this prefactor is determined. There's nothing, there's no parameter here. Yes, there's just the scattering length and the dipolar length in this expression. Nothing else. Yes. And so, yeah, you have to have these prefactors right. That's why you need good theory friends that tell you, yes, this square root of pi is really there and so on, because now we are going to fine-tune the parameters, and it's really important if you want to understand your phase diagram, what these prefactors are. Okay, but this is now predicting droplets or bound objects even that exist even if you have no trap. So just like a liquid water droplet or liquid helium droplet that is stable in itself. That's sort of interesting. That's what quantum droplets are, yes. So I just I tried to explain to you already what is shown on this slide. If you have a dipolar mean field that is attractive pointing this way and a repulsive contact mean field, then they can almost compensate each other, and then this Li-Huang-Yang correction here, yeah, makes all the difference. Yes, it will stabilize the system.
For chromium, is that really small?
Yes. So now the question is, at which densities do you get this this stabilization effect? And it turns out for chromium, the densities are so high that you are lost by three-body collisions that are, of course, also there. But as you have this stronger dipole moment now, the stronger dipole interaction, we are just lucky, yeah, that this atom, dysprosium and erbium, the stabilization sets in before the three-body kills it. Yes. Okay. Yeah. So here's the effective equation again. Now with this psi to the 3 term, I just abbreviate this here with this little g quantum fluctuations. And of course, we can discuss, yeah, what is it that makes this repulsive? Yeah? What fluctuations are we talking about? Actually, it's these are the phonon excitations in the PEC. Yes. If you think about an infinite PEC, you will have a dispersion relation. You have low energy excitations, low k phonons. Every phonon is a harmonic oscillator, and every harmonic oscillator has a 0-point motion. So these phonons, even if you are at 0 temperature, these phonon modes are fluctuating. And if you integrate over this contribution of all the phonon modes in the correct way, which is not trivial, because you have to renormalize your integral, which otherwise just diverges, that gives you this repulsive term. Yeah. So in a way, I mean, some of you have maybe studied the Casimir effect, yes, between two plates in the case of electromagnetic field, yes, where if you not consider what happens from outside, you just consider what the modes inside the cavity do, the vacuum modes inside the cavity do, they will repel the two mirrors. Okay. It's just that the same effect from the outside is even stronger, and as an effect, the Casimir force pushes it together. Yes? So this is my intuitive understanding of what is going on here. You have the vacuum of phonon modes inside, and that leads to the repulsive force that stabilizes these objects. So if you now do the experiment, you can do a PEC, let it release it from a trap. Yes, then a normal PEC will just do this. It will just expand. Yes, as you all know from time-of-flight experiments. Yes, the internal energy is released and the atoms fly apart. But if you are in that droplet regime, the self-bound droplet regime, this is not happening. Even if you have no trap, the atoms decide to stay together, like a liquid, yes, like a real liquid. Yes. And what also reminds you on the behavior of a real liquid is that if you now increase the atom number, I show you here the size of the droplet along the magnetic field direction and in the radial direction here for different atom numbers. So if you have a small atom number, well, then you have a sort of Gaussian shape of that droplet. Then you increase the atom number, then you will hit a saturation density at some point. And from that point on, the droplet just grows, just like a normal liquid. If you double the number of atoms in a water droplet, the volume will just double. And the density is no longer growing. Yes? So this is exactly the behavior that these quantum droplets also show. Okay, so here's another slide about the experiment. These self-bound droplets, they are elongated along this magnetic field, just like in this movie that I showed at the very beginning with this ferrofluid. You know, the equilibrium shape is elongated. Yes. And this in the experiment, we are looking from the top on these needle-like droplets, and we can switch off everything yet after we have prepared them in the right shape with our dipole traps in this elongated fashion. And then they will just float around in our chamber, yes, without any trap. Of course, we have a little bit of a levitation field that they don't fall down. With a magnetic gradient, we can do that. Otherwise, they would just drop out of our focal plane of our observation. Yes. But you see that they are staying there for 70 milliseconds, and then something interesting happens. They are losing atoms all the time due to free-body losses. So they slowly become smaller and smaller, and eventually they make a transition to the gas phase again. Yeah? And from that point on, they start to expand. So there's a phase diagram for these droplets, which has a critical number. The droplet has to have more than a certain critical number. Otherwise, they are not staying together. And we measured in this paper the critical number and so on. That's a good way to test the theory. Not going into the detail of that. This droplet formation has by now also been seen in not only erbium in the Innsbruck group, but also in a two-component gas, in a two-component BEC. Because there you can also have two kinds of interactions. One is the interaction within one component, and the other one is the interaction between the two components. Let's say you have a mixture of KRB or so, yes. Well, no, KRB is a fermion. Let's say you have a two bosonic, well, you can have a boson mixture, right? KRB. 39 and 87 helium would be a Bose-Bose mixture. And if you tune the parameters, and that's what Letizia Caruel at Pfau in Barcelona has done, then you can also come to that regime where basically the one interaction compensates the other one more or less perfectly, makes it a little bit negative, such that the system wants to collapse, and then the quantum fluctuation term kicks in and stabilizes those droplets. So this mechanism of forming these quantum droplets is very general. It's not only works for bipolar atoms. There you have the two interactions within one component. And you can also tune the parameters in a two-component system to get into this regime. And actually, that was what Dima Petrov predicted in this paper down here in 2015. Okay, now you can play with it. Yes, you can make a lot of these droplets. You let them release, and you see every individual droplet is a magnet. Yes, so if you have many droplets, they repel each other, of course. Yes, just like classical magnets would repel each other, and you can observe that they fly apart if you lower the confinement. Yes, or you can take an array of droplets and squeeze it a little bit, Then you observe the chain of droplets breathing and so on. Yes, we can play it out now. Yes, with these objects. Good. So this whole field of quantum droplets is a field on its own by now. Yeah, lots of people work there, also in theory. But for today, I mean, I want to leave it with this and move on. Okay, so there's this overview article that we wrote 2019 about this. And move on to the next topic, namely, if you have many droplets, can you form a supersolid? Now, what is a supersolid? In very simple terms, yes. I'm a simple-minded guy. I always need a very simple explanation. Yes. So if you think about a phase diagram like this one, where we have a temperature and one control parameter, let's say this is going to be our epsilon. That's this ratio between contact and dipolar interaction. Yes. Then if you are contact interacting, then you cross TC at some point and the Bose-Einstein condensate forms. And if you have an infinite container, the wave function is just flat. That's the first symmetry breaking that happens if you form a BEC. It's a so-called U1 symmetry because you're generating a phase here. Yes. Now, if you are changing the control parameter, so that's a U1 symmetry breaking. If you're now changing the strength of the dipolar interaction, we have seen that the system has a tendency to form structures. Let's say in one dimension, it just forms a modulation here. Yes. So if your ground state now, and that's important, we're talking about ground state phases, yeah, has a modulation on top of a background here of a normal superfluid, then you have created a state which has fluid behavior due to that lower part here, and crystalline behavior or solid behavior due to its periodicity in the upper part. So a supersolid, in simple words, is a quantum mechanical superposition of a solid state with periodic modulation and a fluid which has no modulation. Yes. Now, obviously, if you want to build such a state, you have to have interactions because such a modulation costs energy. Yes, if there wouldn't be any interaction, this is kinetic energy. Yes, this is why even an ideal BEC is just flat. Yes, so you have to have interactions, and the dipolar interactions are going to be the ones that are doing that for us. Yes. So there's a second symmetry breaking going on here. That's important, yes, because every symmetry breaking in a phase diagram later on leads to elementary excitations, so-called Goldstone modes, Higgs modes, and so on. And we have two of them here. We can, if we have time, I'm not sure, Peter is already nervous. We can discuss that over the hike, I guess, if you are interested. So here is the ground state that we are looking for. The supersolid is a superposition of two macroscopic wave functions. One is flat, that's the fluid part, and one is modulated, that's the solid part. And that's important now, because we need to have that connection between the droplets here, such that the overall state shares the same phase. If we only have the solid part, yes, and they are not connected, yes, like in these movies that I showed you in the ferrofluid, these droplets were totally isolated. There was no connection anymore. Then they will very quickly lose their mutual phase coherence, and this is just solid. This is not a supersolid. Yes? So we have to find parameters where this modulation is not going all the way down to zero. Okay, so here are some pictures, of these states that you can produce just to convince you that we can make such trains of droplets and we can observe them for half a second or something like this. So, I mean, now we are looking more deeply into those structures, whether we can find parameters where they also behave in a coherent fashion. Okay, so let me just speed up a little bit. So basically, if you do the theory now, in a trap for certain parameters, we have this extended Gross-Mitaevsky equation. We can predict what happens. Yes? And then you find that for certain scattering lengths, we actually would expect such a coherent superposition, where the modulation is not perfect yet. Yes, you see that okay, structure is forming, but in between the droplets, there's still some connection. Yes. Whereas if you go further down with the scattering lengths, you finally end up with isolated droplets where that have no connection anymore. Yes. So these are then in the lower row in situ images of exactly this situation. Yes. So you can convince yourself, okay, this structure formation actually works like planned. But of course, you have to prove now that you really have phase coherence, and the way to do this is to do time-of-flight expansion. Yes, interference experiments. Yes. If your ground state looks like, you know, a triple slit or something made of 4 droplets or so, and you release it, and they are phase coherent, you expect an interference pattern. Yes. So I'm not going into the detail, but if you look at this interference pattern, you see the diffraction orders. And if you analyze those diffraction orders in a statistical manner, actually, then you can convince yourself, yes, the state that you have produced here is actually phase coherent. Okay. Good. How much time do I have left? Now we have a super solid, and the one thing that I wanted to tell you is an interesting method, basically, how we can now observe these elementary excitations, in particular this rotor. How does it look like? I was showing you a picture of a rotor already, but that's not how it looks like in our experiment. Yeah. So how can we get access to these excitations? Now, remember, we take in situ images. And if you take an in situ image many times, you repeat the sequence, then every image looks a little bit different. Yes? So there are fluctuations in the system. And now we want to analyze those fluctuations, because the fluctuations are directly connected to elementary excitations that you have in your system. So if you take, for example, of that supersolid here at a certain scattering length here, a lot of pictures, hundreds of pictures, yes? Then you calculate the mean image of all these 100 images, and you calculate then the deviation of every individual picture from that mean image, okay? Then you get images that look like this here, yes, in this regime here, okay? Now, you can look at those, and first thing that you can realize is that there's structure here. Yes. For example, here around the supersolid regime, in particular, these fluctuations resemble the period of the supersolid. Yes. So one way to analyze is to take the Fourier transform of the modulus squared of that deviation, and that is, if divided by the number of shots, what is called the structure factor, the static structure factor. That's a quantity that other people, for example, in neutron scattering, derive from their scattering experiments. We derive it just by in situ imaging. We are doing a real space experiment, not a momentum space experiment. But we can trick the Fourier transform, yes, and then get the momentum space information. So these are how these structure factor pictures actually look like. And now we can take this structure factor that has been widely used in the literature, of course, to characterize such many-body systems, to connect it to our excitation spectrum. So Feynman, for example, was someone who has thought about this a lot. in the context of helium and its excitation dispersion relation. So here you see a dispersion relation and the corresponding structure factor as a function of K. And if you now do what we always do, we reduce our, we increase our epsilon such that we get dipolar effects, then the roton appears, and as this roton mode is a soft mode, which is very susceptible to fluctuations, the structure factor will develop a maximum exactly at the momentum where the roton minimum appears. Yes. So if you go further, it almost touches zero. You see that the structure factor has a maximum at this position. Okay. So that is a very useful tool. Yes, if you want to extract the excitation spectrum of our BEC supersolid, or also the of the BEC or the supersolid, or we want to follow the whole transition, you know, for this roton to soften and eventually touch zero, then looking at these fluctuations is actually a very easy way to do that. Yes, we have these pictures anyway. So we learned actually all of this from Martin Zwirlein, yes, who was spending his sabbatical with us. First in person, but then mostly remotely because of the pandemic. But we were very lucky again, yes, that he joined us on a weekly basis in our group meetings for more than a year now. Yeah. So he's an expert in physics, yes, and he told us about the connection now of that structure factor that is measured here. That's a measurement as function of the scattering length. We can measure the structure factor of the state that we are seeing. So we can follow this all the way up. And at some point, when the fluctuations are maximum, this is when the phase transition happens to supersolid. Yeah. And you can now use Feynman's formula, which connects the structure factor to the dispersion relation. One has to be careful here. Yes, only if you have a single mode, basically, that is excited at a certain momentum. This is a unique mapping. Yes. But on the BEC side, before the roton touches zero, that is a good way to, you know, convert the structure factor into a dispersion relation. And then there is a factor that you know is described here by Feynman and Bield, which connects the dispersion relation with the temperature. Yes, you assume you have a thermal ensemble, and it has a temperature, and it populates those modes thermally. Yes. Okay, so you can invert this. So we measure that S of K, so you can invert this to extract the dispersion relation. Okay. So if you do that, you get the excitation energy as a function of momentum for the scattering lengths. And if you follow this down, you see, of course, well, not of course, but that's what you get, that the roton is forming. Yes. You can see the roton minimum here. And you see also that actually we observe the phase transition way before the roton touches zero. That has to do with the finite size of our system, because there's a 0-point energy in the system, and we have a finite energy. So we can follow this dispersion relation up to this point, and from that point on, we start to have a ground state that is already modulated. So it's not only fluctuating; it's already modulated even in the mean image. Yes. And from that point on, the single mode approximation does no longer apply. Yes? Because if you have a periodic structure, you have a Brillouin zone, you take the modes that are at higher K, you fold them over, and then at 1K, basically, you not only have a single energy that is possible, you have many energies, bands, basically. Okay, now this looking at the fluctuations has yet another advantage. Namely, you can look at what is called the principal components of the many pictures that you get. Yes. And if you do that, then you can get a direct image of those excitations. Yes. And we see in our case, we have principal components that come in two flavors: the symmetric roton, which is symmetric around the center of our trap, and the antisymmetric roton, which is antisymmetric with respect to the trap axis. Okay. So the roton that we have in that system is actually a degenerate one. It has two branches, a symmetric and an antisymmetric one, and only if the supersolid is forming and you know, in a finite system prefers one symmetry, then this degeneracy is lifted, and one of these modes connects to a Goldstone mode, and the other one to a Higgs mode. But again, we can discuss this over the hike. Okay, so you get a direct image experimentally, and it's an experimental image of a roton mode, and you can compare it to the Pogolubov-Dijen, you know, calculation of how this should look like. That's the line here, and you almost see no difference actually. A very good agreement with theory here. Yes, that's the Pogolubov-Dijen theory. Then if you take higher, so the thing about principal component analysis is, if you have a dominant mode like this roton mode, okay, you get this as the strongest principal component, but you can still look at the next one, or the weaker ones that are also in your data set. Okay, so for example, the BEC quadrupole mode, which is the sort of lowest order phonon mode of the superfluid part now. Yes? Or you can look at modes like this, which are the crystal phonons. Yes. So all of this is in the principal components of the fluctuations that you see, and you can measure their weight as a function of the scattering length. So when you see that on the BEC side, the BEC phonon is dominant, and the crystal phonon is basically not there. Then if you come to the supersolid, they become equal in strength. And then if you go to the isolated droplets, the BEC phonon is basically gone. Yes, and you only have crystalline. And that's actually the nature of the supersolid. In that region here, we have excitations of the fluid part, which is the flat part, and excitations in the crystal at the same time. So two kinds of sound modes basically simultaneously present in that state of depth. Okay, yes, and this is just the crystal phonons. They show that interesting structure. Here you see that there's a brilliant zone, and you see the mirror image on the other side of the brilliant zone. You basically see the folding of the edge of the brilliant zone. Okay, so far to that, and now the question is, what else can you do? And in the beginning, I showed you these fancy structures, these labyrinths, and so on. Now, if you have that Gross-Mitaevsky equation with this stabilization term, you can play around with this, at least numerically. I have a very good student, Jens Heldkorn, who is doing that. And he predicts now ground states that have fancy shapes, yes, in 2 dimensions, because everything that I have shown you so far was just a very elongated trap, such that we have a droplet array in 1 dimension. Yes, they are just sitting side by side, but they are not able to move in the second direction. Yes, but if you open the trap and make it a pancake trap again, and you ask yourself, you know, how do the structures look like there, then you get pictures like this. And you can come up with a phase diagram. This is atom number, this is the scattering length. You see there is a super solid, that's the blue range of this phase diagram at small atom numbers. That's where we are, unfortunately, right now with our experiment. But obviously, we want to go with our experiment into this region where you see voids instead of droplet arrays. So I should say, here, you see there are these stars. Here we get 2-dimensional droplet arrays, 2-dimensional droplet crystals, which is maybe what one would expect from going from 1D to 2D. Yes, I mean, instead of having the droplet arrays in 1D, we can now have them in 2D. Yes, but it's much richer than that. Yes, if you go up here, then the structures start to look like this. They have these voids now. which are connected by a superfluid. Or if you go to this red region here, then the ground states actually look like these labyrinths that I have shown you in the very beginning in the movie. And it turns out, I mean, these structures, one of these structures is not the only ground state that you can have. There's a whole zoo of such structures that are all more or less up to the less than 1 Hertz level, basically degenerate with each other. So what you would expect if you do an experiment in this regime is that you have a labyrinth structure that is sort of meandering around and flowing around very slowly, just like this movie that I showed you at the very beginning. Okay, so with this, I'm at the end. I show you this movie again. We hope we can do that at some point in the lab with a real superfluid, yes. And I wanted to thank the team here. They have been working hard, and in particular, Martin for his help over the last year. Thank you.
That sounds like you mentioned that you probe like the coherence between like the
Yes.
solid and the superfluid. The ITAMP, like, can you explain one thing like how you did this?
Okay. I actually have somewhere extra transparency, but it takes too long. So what do you do? Yes, and it's a very good question. Yes, because a single interference pattern is not enough to do that, because you will see structure like this in a single pattern, even if the phases of the different droplets are different. Now, what you have to do is you have to take many of these pictures and ask yourself, is it stable over many shots? And do a statistical analysis of the weight of these diffraction orders to convince yourself that the phase was stable for every realization. The phases over from one droplet to the other was the same. Yes. So it's really a statistical analysis. We can go through it. I have somewhere I have a slide that I could show you exactly what we did. But it's important that a single diffraction picture like this is not enough to convince yourself that that the system is stays coherent.
I have a question.
When you generate these droplets, do you have a scheme of getting rid of like background storage, or are most of the actually formed droplets?
Yeah, I mean, if you start with a condensate that is way below TC, then it's more or less all the atoms that we can convert into droplets. Only the thermal atoms sort of evaporate, let's say. Yes.
So you start to do like
yeah. So let me show this again. I think you can imagine one of these pictures. I thought you can see this here. Yes. So if you look at this picture here, you see a little bit of a thermal cloud at T equals 0. Yes. You don't see that thermal cloud here anymore because the thermal atoms just, of course, fly away. Yeah.
Just the way you form the droplet, I imagine you have like this cigar shape droplet potential, and you have this heavy interaction, and you have this Lemoyne the package that is stable, right? But then at some point you want to open up the pancake. So you like remove this cigar shape potential, and how do you get the
No. Okay, yeah. So you have to think first, how is your droplet look? How does your droplet look like in free space without a trap? And then you want to have a trapping situation that is as close as possible to that. Otherwise, if you release an arbitrary shape, it will start to breathe a lot. Yes. So you don't want to have a lot of internal excitations around that ground state. So that experiment is designed such that we are shaping the trapped droplet to the shape that it has in free space already. Yes. And then it's not really breathing a lot. Yes. So we are not, I mean, these droplets are really released without trap. all the other pictures that I have shown you before, the many droplets, maybe that's what you're referring to, they were still in travel.
So in this picture, they are really like just in free space, but with a little bit of adaptation against gravity.
Here, the only thing that is left is gravity and the magnetic field gradient. Yeah, that's
Actually, showed this mathematical method, the appearance of the rotor with different
scattering length.
and there was like another dip.
Okay. Yes. Okay. So let's look at the structure factor first, maybe. Let's see here. Yes. So if you follow the structure factor up to the phase transition, yeah, there's a single maximum, and if you then continue, you can measure the structure factor even across the phase transition. Yes, you cannot do this mapping, but you can measure the structure factor. It's just an experimental thing. Then you see that around the beryllium zone, which is this dashed line here, yes, you get actually splitting into two maxima. Yes. Is this what you are referring to?
Actually, I think it's the next.
Okay.
Yeah, this one. Like this would be a wiggle, like or like this.
Oh, this guy.
Yes, exactly.
Okay. Yeah, that goes back to this feature here. You can see that there's a little bit of a hump here. Yes. I can't tell you what that is.
Let's thank you very much.